that's the title, Taxonomy of Ruby Calls. First slide, gotta feed my ego. So this is me. I'm just a guy, mostly a guy. I became a Ruby committer in 2019, and I worked on YJIT since day 0, and I have a little Japanese skit here. Sorry if you don't speak Japanese, don't worry, you won't be missing anything important. で、空便でカナダから来たんですね。来たらご飯屋を探してたんですよ。良さそうな日替わりセットを看板で見かけてお店に入って注文したんですよ。日帰りセットをくださいって言いました。誉れのあるご注文できなかったので英語に戻ります。So why have this talk? The title and the slides are in this slide are the only place I will mention the word taxonomy, since I don't want to pretend that this is more serious than it is. It's just a bunch of groupings of different calls I came up with. I like the animal analogy because the calls are like abstract animals with unique behaviors. So welcome to the zoo. I hope you enjoy. Since calls are everywhere in Ruby code, language changes usually end up touching them. And there's been at least one change to call features in the past 6 years of Ruby releases. And I hope that these categories give you a unique view into Ruby semantics that may help you understand language changes or show you corners of the language you didn't know about. For practical development purposes, you can use these to come up with test cases. And both the process of making categories and the categorizations that you come up in the end will help with finding bugs. So my categorization is based on the nature of the work required to pass arguments in the call. In summary, go past the parsing phase, also go past the method definition phase. This is what happens when you're making the hop from caller to the callee. And I'll be assuming that we know both the caller and the callee. So the starting calling side and the side receiving the argument. There's some subtleties in finding where the call should land, but that's for a different talk. Argument passing. Now, obviously, using different features at a call site will do different kind of work, but who you are calling also matters a lot. In this foo example, the version of foo that takes a rest parameter requires an allocation of an array, but the second one doesn't. But the caller side is the same in both cases. Now, if we analyze the body of the method and see that it doesn't use a parameter, we could say that, oh, if you're not using it, why pass it? There's no work required for passing the argument. Also, depending on the usage, you can work backwards to optimize the exact way you're passing the argument. But these are somewhat second-order effects. And for most of this talk, I'm just putting the parameter list here. It's incomplete Ruby code, but it'll help us focus. A lot of this is CRuby specific, so when I say something happens, just know that the whole talk is a mix of implementation concerns and language semantics discussions. Now, to make a call pair, you would pick a feature you want on the caller side, and on the callee side, like in the sandwich shop, you can pick multiple features from each side, so you have a combinatoric explosion. And do the exact counting exercise to find the exact number of combinations possible, but it's not quite the power set, since some features are mutually exclusive. Making this table was a good exercise, but I realized that just like picking combinations off of it wouldn't be super engaging. But luckily, this isn't the full story. The features you use are sort of the syntactic form of the call pair, but at runtime, depending on the nature of the things you're passing, a lot of things can happen. So many features work differently depending on the actual arguments you pass. I picked splat, so star args here, because there's a lot in there. When args is in an array, there's a whole conversion protocol that happens that sometimes involves calling into a separate method. So it's like you get 2 for 1 when you call a method. Also, what's inside of args also matters, because sometimes you need to check the last element in the array you're splatting, just in case it's a keyword, Ruby2 keywords hash that turn into keyword arguments. We care about exactly what happens in these data variant features, because this is a way to find optimization opportunities. For example, you can optimize by specializing argument passing for each known call pair. So this is some excerpt of argument passing code having to do with splat. Don't worry too much about actually parsing and understanding the code. The point is just that it's doing a lot of check-in there about, okay, what is this caller using in terms of features? What is this callee doing in terms of features in the parameter list? If we specialize based on one specific call pair, you don't have to do any of these check anymore. Or you can think of it as bundling up all the check into one. And if you do this reduction, the code gets simplified into something like this. Calls are fairly static in Ruby programs because it's what you write, and despite all the meta programming features and dynamic features of Ruby, most of the time the code stays static throughout your runtime. And this transformation removes the static parts, leaving only the runtime checks on the inputs. In this case, it's checking the contents of the splat array. The reduction sort of leaves behind the essential work for argument passing for the specific thing you specialized on. Ruby2 keywords checks are left over, and that shows that every splat call has to check the end of the array, just in case there's a keyword hash in there. Ideally, when you don't use a feature, you don't pay the speed penalty for it, but that's not the case for Ruby2 keywords. Even if you don't have any mention of Ruby2 keywords anywhere in the entire Ruby code that you're running, we still have to do this check. But anyways, you need a pretty complex JIT compiler to do this transformation mechanically. And this is not a JIT talk. This is just a way to tease out semantics out of the implementation. And I'm using it to come up with my categorizations. By the way, there's a mechanism in the interpreter called fastpath that basically use this. It caches a function pointer that does argument passing logic specialized for each call pair, and the body of each of these functions are more or less the output of one kind of these reduction. The rest of this talk is just categories I made up. The first one is sort of the base case. It says it does no work for argument passing per se. Sasada-san designed the VM so that callers compute arguments and put them on the postfix notation stack in the exact layout required parameters want. And this happens before the actual call on the caller side. When the call happens, the arguments are already in the right place, so there's no need to move them or copy them anywhere. You can see that there's some extra metadata on top of the arguments, but 1, 2, 3 don't move. The metadata turn temporary values on the caller side into local variables on the callee side without actually moving them. I'm using simple integers for this example, but this works for all expressions you can come up with to compute your arguments. This is a somewhat fundamental protocol the whole VM is designed around. These are the simplest kind of parameters you can have, so it makes sense to have them fast and efficient. Sometimes we have to move stuff, though. That means the postfix notation stack can be smaller after the call than before the call. There are quite a few features that can do this, and I listed some examples up there. Basically, anything that requires discarding of arguments, like unpacking an empty array or gathering multiple arrays into one object, and do this. We always want to know the stack size after the call because you need to do stack overflow checks. But also, there are cases where widget needs special handling for shrinking. Computation in the VM always use values at the top of the postfix notation stack as input. This is just how VM operations are defined, and widget follows this while handling calls. So once it's done with an argument, it wants to pop it off of the top of the stack and move on to other arguments, which again is at the top of the stack. Calls that pass a block argument has it at the top of the stack. So it's the first thing that widget has to deal with. Now, one way to handle is to predict where the block argument will go, pop it of the stack, move it into the right place, you're done. And that's what happens on the left. But sometimes this won't work if the stack needs to shrink because the final destination of the block argument is where another argument is. So in this case, when the stack shrinks too much on the right, 1, 2, 3 gets gathered into an array for the rest parameter. That ends up where 1 is on the right side. But the final location of block arg is where 3 is. So we can't move it as the first step because we still need 3 after we're done with block args. So to handle this properly, widget needs to tuck away block arg while processing other arguments. It needs some temporary storage in addition to the stack, or it needs to move away from this typical model of always taking from the top of the stack as input. Well, actually, neither of the cases work. Actually, moving up past the top of the stack isn't correct in all situations. And widget has a bug in there I found while writing the slide. The GC doesn't mark values above the top of the stack. So if we yield to the GC after the move, the block argument will be collected. Maybe widget needs to move away from using the stack as scratch space during calls to handle this properly. Next, I have a category that's the polar opposite in terms of complexity. When you use splat, keyword splat, and object block arguments, the ampersand, they each expect array, hash, and proc, the classes. When the argument isn't the right type, we try to convert it by calling a conversion method. There's some differences between the 3 conversion protocols, but there's some things that are the same across the board. When you pass nil with these features, you end up passing nothing. No special status is actually relatively new. Block arguments treated as specially at first. It was an error for keyword argument splat. And Ruby 3.4 made it work for keyword splat. And in the next Ruby release, it should work more reliably for array splat. Right now, the pass nothing effect for a single star nil relies on getting an empty array back from calling 2a on nil. So you can redefine 2a on nil class to break it. The next version won't have this extension point because it doesn't seem very useful outside of a trick, maybe. We'll always discard nil without calling anything. Now, when we do call the conversion method that can fail, The method might not exist, it might not return the right type. Usually we end up raising argument error, but array splat is special. When the conversion fails, you pass the argument as if you didn't do any splatting at all. It's like if you edited the source code and you just remove that star. So, and this effect falls out of 2 steps. First, it tries to do the conversion and it fails. And to handle that error, it wraps the failed to convert object in a single element array. And then, like usual splat situations, it unpacks the array. So you're wrapping the array and then unpacking it. You end up with what you started with in the beginning. Somewhat of an odd feature, but maybe it's not fully intended for use. It's just a side effect of being consistent with the capital A array method on kernel, which also does this when the conversion fails, it wraps in one element array. Now, onto block arguments and refinements. The ampersand symbol shorthand is pretty well known. It's useful when you need a block that takes one argument and just calls a method on the argument. Instead of writing out the block, you can pass the name of the method that you want to call using ampersand instead. I'm using downcase in this example, and 2 lines give the same result, as you can see. Great. I used to explain block argument conversion as, oh, it's just calling toproc and using the proc from that, and you can call procs, and it's all great. So for symbols, it could be, we could redefine the toproc method on symbol as something like this. It's returning a lambda that takes one parameter and calls the method with the same name as the symbol. Now, my symbol toproc implementation does work. And if you plug it in for this example, you get the exact same result as if you didn't overwrite the definition. But what if you have refinements? We're in a scope that redefines kernel itself inside the refinement scope. And this, the usual definition of itself just returns the receiver, so the output is identical to the input, but in this redefined definition, we get 1, 1 instead, because I have itself returning 1 inside the refinement scope. Just like the downcase example, the symbol block argument shorthand behaves exactly the same as if we wrote out the block by hand. It maintains this parity. But if you use the re-implementation of symbol, that's going to break it, because the public send is in a different lexical scope, so it won't see that it needs to use the refinement down there. And it might actually be impossible to re-implement symbol toproc in Ruby, because there's no way to get lexical scopes as objects in the language. Now, here's some more evidence that symbol block arguments do more than just call toproc. We can call toproc on a symbol and get an identity function proc. It just returns whatever you pass it, 0 in this case. Now, let's have the same redefined definition of itself again. We can call the proc created outside of the refined scope, inside the refined scope. And the refinement does have influence, so we have 1. We get 1 back. So far, you can still explain this as ampersand calling toproc. Right? So it seems... Now, let's try the opposite and call toproc inside the refinement scope and then use it outside. This also seems to indicate that it's just calling toproc, ampersand is just calling toproc, because outside of the refinement scope, there's no effect. And So finally, if ampersand is just calling toProc, then by explicitly calling toProc ourselves should behave the same as if we use ampersand. So here I used ampersand and captured the proc object, save it into a constant, and then I used the proc outside of the refinement scope. So it should return the same result, but obviously it won't return the same result if I made the slide. So it's doing something extra than just calling the toProc method is the point. Wow. In summary, conversion procedures gets quite complex, both when conversion succeeds and fails. Conversion happens relatively rare though, and as we saw, there are situations where it doesn't call a method, like in the fail to convert array case. Passing a symbol as block argument usually doesn't make a method call either, unless you redefine symbol toProc. Now, I want to point out that just because there are fast ways to implement things doesn't mean that the implementation is simple. The complicated parts of the semantics don't disappear, and they sometimes manifest as memory usage or bugs. And I found a crash while making the example program, so if you try and run it, you might get a crash. Also, I have to admit that I'm being kind of lazy with the categorization here by lumping all of these into just conversion. Really, you can split this down further into like array conversion, keyword argument conversion, block parse conversion. I'm running away the work like when widget sees complex situations that it can't generate good code for. Okay, let's take a break and talk about something simpler. Mizonomimasu. And when you make a call with some arguments, say 1, 2, 3, you would expect that the caller gets 1, 2, 3. But this is not completely true in all cases. Sometimes there are extra data you're passing. The most basic example is when you call a method without passing a block, there's a piece of little data in there that says, oh, I'm passing no block. But this that isn't exactly object that the callee has access to. When the callee has optional keyword parameters, Ruby needs to compute the default value for all the keywords the caller isn't passing. So for this example, we have 6 sets of calls to the default ABC method to compute the default values. In general, for n optional keywords, there are 2 to the power of n ways to compute the default values. For each optional parameter, you can either pass it or not pass it, describable with a bit. So with enough bits, you can describe the status of all the parameters. The magic number is 31 at the moment, but the point is, a lot of the times, the VM passes a hidden integer for optionals. If the callee has too many optional keyword arguments, keyword parameters, we use a hash as a fallback. But in any case, there's no way to directly get the integer or the hash, so it's hidden. It's set up as part of the call before running anything in the callee, and the callee then checks, then refers to that to figure out which default computation it needs to run. Another category of call data that passes hidden data is for forwardable parameters. This started to pass hidden data in 3.4 to reduce GC allocations, thanks to Aaron Tenderlove Patterson. He coined the term forwardable and forwarding. Basically, you can define the parameter of a method that you are able to forward, but you don't have to use it. But if you do use it, then you're forwarding. Forwarding should preserve the argument, so it should behave as if you didn't have the intermediary in the middle and you just called the callee directly, like in the bottom. Different call pairs require different work to handle. So intermediary has each caller pass a description of the call site, along with the actual arguments. Internally, this call site description is called call info and includes things like the number of arguments, the kind of features used. Usually we're done with this information after the call, but in this case, the call info itself is an argument. So kind of meta. There's no way to get the call information inside intermediary as a Ruby object though. So it's just hidden data. It's only used when you actually do the forwarding. And by the way, the top diagram has intermediary looking like a bottleneck that the 3 calls has to fit through. And that's intentional because forwarding calls are harder to cache than usual. Usually you can cache based on the call pair, but in this case you have an extra call info that you also need to, that's also relevant to decide whether you can use a fast path. So it kind of blows up your cache key. And finally I have a category for allocation, and Jeremy is talking about this in the main hall, so maybe for this class, just get up and go to the other hall. But anyways, I'll try not to overlap too much with Jeremy here. I'll start fairly abstract and work my way back to what CRuby currently does. First of all, when something allocates, whether something allocates has always been up to the Ruby runtime you're using. Ruby code works with Ruby objects, but the code doesn't have explicit control over the in-memory representation and the lifetime of the memory. There's no way to immediately free a Ruby object, for example. Now, in this example, I have a call pair that involves a rest parameter, but the body of food is a mystery. I want to know whether it's necessary to allocate an object for this call pair. But it is necessary because the body of food can do anything, including stashing away the object into a global variable that makes it live forever. So you have to allocate. Now, if we know the body of foo, then you can say that, well, it only needs to service the first call, and then we're done with the data. So the caller doesn't have to allocate an object, it just make something that works for the first call, and then it's done. But then in the final case, it's passing args to a mystery method. Now, then again, because we don't know what the mystery method can do, it can do anything, and anything includes making the object live forever. So again, we need to allocate. So yeah, there's some analysis you can run to pick alternative memory management strategy other than allocating an object up front. It requires a pretty complex analysis to figure out. And because you can load Ruby code at runtime, this analysis also needs to happen at runtime. And also, as we saw, the scope of the analysis matters. Depending on it, you get different results. Takes quite a bit of sophistication to get performance win out of this. We'll try to do something for ZJIT. But anyways, well, on paper, there are many situations we don't have to allocate with the GC. We can't do it yet. There's obvious situations where you have to allocate, where the parameter basically calls to an object, like rest keyword rest. There's also some C method definition options you can use that basically act the same. But there's some surprising cases where it allocates even though in the parameter it doesn't really call for an object, like the hidden hash or integer we talked about with optional keyword arguments. Well, we reached the end. We saw a way to specialize method parameter passing logic to call pair, and a forward-looking part about avoiding allocation. There's also, of course, all the categories. I'm not any kind of authority when it comes to these categorizations, so it's pretty arbitrary. I just made them up. Also, so I encourage you to come up with your own categorizations. The exercise seems useful. I found 2 crashes while making them. I hope you have fun at the zoo, and thank you.